Okay, let's implement time embedding first. We first need to define the parameters that it's going to be just W, grades, of course, you need to create layers. It is first none. How do we implement the forward method? The shape of axis is going to be like this. Because embedding receives a sequence of numbers indicating the class number. So the shape is going to be n comma t. And v comma d is self w shape. And the output should be this shape, because n samples, number of batch, t times that, d is the dimension of the word vector. Initialize layers before t in range t. We create an embedding layer like this. And we're going to use the same weight. Therefore, we pass the same weight again and again. And the output at time step t is going to be layer dot forward the current input. And layers, we're going to append the current layer like this. And return now. And how do you calculate the backward? Because d out should have the same shape as forwards out, this one. The shape is going to be NTD. And first, we initialize grade as Z at 0, 14 range T. Now in this case, each embedding does not affect other embeddings. Therefore, we just retrieve layers one by one rather than in inverse order, reversed order. Like this. And the only thing we need to do is just accumulate gradient from all the layers. And then, because they don't affect each other. However, because W is used for all words, and we need to collect all the upstream gradients from all the words. And we store the accumulated gradient and we return none because we received this XS. This is the input. And how do we implement time of find? The parameters are W and V. Gradients are NP zeros like W, NP zeros like V. And the shape of XS are like this. One thing you need to remember to process a sequence of vectors is we need to vectorize them for efficient manipulation. So we're going to reshape XS as just a long vector like this. Why do we do this? We implement the convolution in this way. And by using this operation, we don't need to use any for loop. And the output is simply np dot rx w plus b. Here we're using broadcasting and single instruction multiple data vectorization. And we return by reshaping our output as n, t, and the rest. And what about the backward method? We first retrieve xs like this, the shape like this, and d out refers to reshape for vectorization like this. Rx like this. We've done this a lot. So for this constant, we just sum d out along the axis 0. np dot rx transpose d out dx np dot d out w transpose. And we need to reshape dx back to its original shape. And store the calculated gradients like this. Okay, so this is how we implement time of fine. In the case of time rnn, we needed to think about how we need to pass the gradients to the previous time steps. However, in the case of time affine and time embedding, we don't have to think about those cases. We just need to collect independent upstream gradients and just add them up, accumulate them, and just pass that as an output. Okay, for time soft width loss, it's going to be similar because we don't have internal parameters like this. We initialize them as empty list, cache as cache, none. Here we have something special, ignore label. What it means is our input data might have different lengths. For example, our first input has this length, our second length, this length, fourth one has this length. Then how do we need to deal with this? What we can do is make them all have the same length as the longest one. However, we label them as -1 like this. Then when we calculate the loss, we can ignore the parts with -1. And the reason why we are introducing ignore label is to deal with different various length input sequences. Okay, and how do we implement the forward? We first get the shape of xs like this, and if ts dimension has 3, then it is in the form of one hot vector. And we just turn this into just sequence of numbers. And here we're going to make a mask where TS is not self-ignore label. Okay, so using this mask, we can manipulate the loss, and we don't have to care about these meaningless appendix. Okay, we do the same vectorization. Another vectorization. Like this. And we calculate softmax like this. And we take log. And we need to retrieve only the indices of the ground truth indices, because softmax loss doesn't care about other probabilities, but only the ground truth probability. That should be 1. So that's why we are getting these indices. After that, we multiply the mask. And by doing so, we can ignore the label applied. And loss is going to be minus NP sum loss. And we need to re-normalize the loss because we have different number of data points. And the cache, we store TS, YS, mask, and the shape of axis like this. And return loss. Then how do you calculate backward? We retrieve these values. First, the x becomes ys. The ground truth values -1. Multiply d out. Normalize. And multiply mask. And get the original shape like this. And return EX. Okay, this is basically the implementation of time softmax with loss, time affine, time embedding, time RNN. Using these components, implementing RNN-based language model becomes piece of cake.